Okay, so the problem which we're going to see in today's session is called as n-queens problem. And let me first discuss what exactly is this problem, and then we can discuss the approach in which this problem can be solved, and then we'll try to write a program for this, the approach which we'll be looking at for solving this problem. So this is nothing but, see, this is one of the variant of chessboard like problems. Remember, in competitive programming as well as other competitive events, most often you do encounter problems where they are based on this 2D matrix, and sometimes this is also called a chessboard like problems as well. So this is one variant of such kind of problem. The another peculiar feature of this problem is that this problem is somewhat related to a problem of combinatorial explosion. So we have a concept called as combinatorial explosion. The combinatorial explosion is nothing but, see, it's the phenomena where we have to solve some problem, and in that problem, in order to either optimize, minimize, or in other words to get a solution to a problem, we need to generate various combinations and check is the combinations. So as long as the input size is small, we can manage the combinations, but the moment the size of input increases, the number of combinations which we get for it, they increase exponentially. So at a particular point, we cannot solve all the combinations. So we call it as combinatorial explosions. For n is equal to 1, maybe we will solve with one combination. For n is equal to 2, 3 combinations. For n is equal to 8, suddenly we will be forced to solve about 32,000. For n is equal to 10, it would be number of in the billions of combinations I need to try for. This is called as combinatorial explosion. So I cannot solve it using a computer programming approach. Even if I solve by using conventional computer programming approach, wherever n is less, it can be solvable. But as and when n grows, even computers starts taking considerable amount of time. So one such problem is n-queens problem. We look at this and why we call it as combinatorial problem and how exactly we solve it. See, the problem here is I am given a grid of n by n, and I have to see if the size of grid, for example, here the size of grid is n. Let me highlight this. So size of grid is n. So in this case, I'll have n queens. Now, when I say queens, let us relate this queen concept to a concept of queen on a chessboard. If I consider a queen on a chessboard, for example, let us say this is the queen. If I place a queen on a chessboard, assume that I am on a part of chessboard, and if I am placing a queen, this queen can attack another pawn kept at any on this chessboard, either row wise, right? It attacks anyone which we have it in row wise, or column wise, or it could even attack diagonal wise as well, right? So this diagonal cell and this diagonal and this diagonal cell, and even it can attack any of these diagonals, upper and lower diagonal part. So the problem here is I have n by n grid and I have n queens. So I have to position, what we have to do, we have to find a position for each queen, for each queen, such that no queen, no queen will be in an attacking position, right? What is that problem? Find position for each queen out of n queens, such that no queen will be in an attacking position, right? So if I say it is n by n, right? So I have to place 4 queens, I mean 4 queues. For example, if I place this in this order, okay, so n by n board, and n queens. So if I say, for example, if I say n is equal to 4, then I have a grid of 4 by 4, and I need to position 4 queens in the grid of n by n such that no queen will attack any other queen in that board. So given this condition, given this chessboard arrangement where 4 queens are placed in the way they are currently placed on this diagram, can you say, is this condition met? Can you say this condition met? Can you quickly reply in the chat window? Are the queens on the chessboard placed such a way that no queen is in attacking position to any other queen? Can you let me know? I think screen is already shared. Do you see the screen? I just get a message from Mohammed that screen is not visible or something. Okay, so can you tell me from the current position, what are the positions which are plotted on the diagram? Can you tell me if the queens are placed in such a way that no queen is in attacking position to any other queen? For example, if I want to be further more clear, this would be queen 1, this would be queen 2, this would be queen 3, this would be queen 4. My question is, are these queens placed in a such a way so that no queen in this arrangement is in attacking position to any other queen in the board? Yes. So the answer is they are not placed in that order. So if you see this, if you see here, queen 1 and queen 2 are in attacking position. So queen 1 can attack queen 2 because it is in same column, right? And if you look at q1, q2, they are not in a non-attacking position. But if you see q4 and q3, they are in a non-attacking position. So q4, you can go through diagonal wise, but there is nothing. You can go through column wise, there is no other queen which can be attacked by q4, or either q4 can be attacked by any other queen. So q4 is in non-attacking position. q3, yes, q3 is also in a non-attacking position. It is not attacking any other queen, but q1, q2 are not in a position. So what can I do for that? So can you think of a combination where I can place them? For example, from here, if I move queen 2 to, let's say, can I position it here? No, because it still attacks the q1. So what I need to do, can I put it here? Still it attacks that. So if I put this here, still it attacks. So what I need to do is I need to find out some position here. For example, let us suppose if I place q1 here, and if I place q2 here, right? And if I place q3 here, and if I place q4 at this position. So if I say in this, remember, can this attack? There is no element in this diagonal element, neither in a row nor in a column. Yes, q1 is in a position where it is not attacking any of the other queens. Is q2 in a position? Is there anything in this in its row wise? No. Is there any other queen in column wise? No. Any other queen diagonal wise? No. Right? So q2 is also in a non-attacking position. So q3, is there anything in a row? No. Column row? No. Diagonal wise, there is no any queen in its diagonal positions. So q3 is also in a non-attacking position, which it means it is in a position such that it is not attacking any of other queens. Let us look at q4. So if I look at Q4, are there any queens in the column in which the Q4 is? No. Are there any columns queens in the row in which it there? No. Diagonal wise also there are no attacking queens. So now this position of Q1, Q2, Q3 and Q4 in an n by n grid, it satisfies my solution. What is that solution? Such that no queen will be in an attacking position. This condition is what being satisfied by me, right? So the problem here is to find these position of the queens for any n. N could be any number. For any n, you need to find out, or my program or my algorithm has to find out in which order the Q1, Q2, Q3, Q4 should be placed in their rows, so that in the end, once all queens get their position, no queen should be in an attacking position with any other queen on the board. That's the problem, what we are trying to solve. Are you getting this? Let me know, have you understood the problem? So what is input? Input is n. What is the output? Output is I need to find out the positions of a queens such that no queen will attack any other queen. Have you understood this? Let me reply yes or no. Okay. Okay. So now let us move to the approach. Now, see, one of the quick approach to solve this problem. For example, if I want to solve this problem now, what I need to do is, okay, let us think about some basic approach to solve this problem. How can I solve this? So if I want to solve this, the easiest and the most crude or the brute force approach is to generate various combinations the queens can be placed in a matrix and just check if they satisfy this condition or not, right? So generally when I look for this, see, how do I represent solution? The solution is always represented in form of vector. For example, what do I say is that, so what are the solution I have here currently? What are the solution I have in this for this board? This solution is represented in this one. In which index the Q1 is placed? For example, let us consider if I am talking about this 1, 2, 3 and 4. Let us say if I am representing them by these numbers 1, 2, 3 and 4. If I am representing them by the rows and columns, it is not 0 index, it is 1 index. For time being, just I am writing that, but for a program implementation, we will stick back to 0 of that. If this is the case, solution, how do I represent? Queen 1, at what position queen 1 is there? It is at column 2 in row 1. That's how I represent that. And at what position queen 2 is there? At 4th position. At what column Q3 is situated? 1. At what column Q4 is situated? 3. So this is called as the solution vector of n queens problem, right? So the brute force approach will be, what will the brute force approach? The brute force approach is to generate all possible combinations. For example, it could be 1, 2, 3, 4. So this is one possible combination. What could be other possible combination? It could be 2, 1, 3, 4. And what could be other combination? It could be any combination of this 1, 2, 3, 4. So generate all possible combinations, of this, and check if each combination satisfies the condition or not. This is what I need to check for. If it satisfies, then that is your solution. If it doesn't satisfy, it isn't a solution. For example, does it satisfy the solution? This will not satisfy the solution. But you will find one combination wherein you will find this 2, 4, 1, 3 as one of the tuple in this number of combinations, and this satisfies your solution that no queen in this is in an attacking position. So this becomes a solution. This is a brute force approach. Now the problem with brute force approach is the number of combinations I need to try. For example, if n is equal to 4, if n is equal to 4, how many combinations I get? So how many such combinations I need to try if n is equal to 4? Right? Can you guess how many combinations it will be? If n is equal to 4, okay, so let us do one thing. If I start with a simple grid, in order to be more clear, let us suppose I only have one cell. If n is equal to 1, how many combinations I have? Only one combination, right? If n is equal to 1, I'll only have, if n is equal to 1, the number of combinations, how many there will be? 1. If n is equal to 2, how many combinations there will be? If n is equal to 2, I mean, if n is equal to 2, then this would be the grid we have to solve for. Right? How many combinations there will be? Q1 and Q2. So either 1, 1, 1, how many combinations? N is equal to 2. So see, if n is equal to 2, see, now when you're finding for a combinations, there is a concept called as state space tree, right? So I'll tell you how the state space tree works, for example. So if n is equal to 2, remember, in, for example, what happens is the first thing is, if you position, let us do one thing. Let us write row 1, row 2, row 3, and row 4. If I write this row 1, row 2, and row 3 and 4, and when I say n is equal to 1 and 2, I have the following combinations, right? The first thing is, if x1, if the queen 1, if I store it at first position, right? x1 is equal to 1, then I have, what will be the possibility of x2? What combination I'll have for x2? x2 I'll be putting at second position, right? The second combination is x1 I can keep it at 2, and x2 I'll keep it at 1. So x2 position 1, x1 position 2. So these are the two combinations for it, combination 1 and combination 2. If n is equal to 2, the number of combinations are 2. If n is equal to 3, how many combinations I'll have? N is equal to 3, how many combinations I'll have? So I'm talking about a block size of 3 by 3. This is what I'm talking about, a block size of 3 by 3. So if n is equal to 3, how many combinations I'll have? First element can be placed in, can you guess how many combinations it would be? Let me show you here. So if n is equal to 3, the first element being placed at location 1, right? Then second element, so see, if I place queen 1 at position 2, and in row 2, I have two positions, right? q2 I can keep q3 as well, then 2 it would be 3, then it would be 2. Likewise, it could be first row means 2, then it would be 3, 1, 1. right? So these are the combinations which I'm trying now. So the combination which I want to try for 3 by 3 is the first location within this. If I say queen n has occupied this, then the queen 2 and 3 has to occupy positions in the remaining rows. So overall, if you look at that, then the number of possible row locations and combinations available to you, the total combinations you will have is 6. So in short, the number of combinations which are available to you based on the conditions for this, see, the based on conditions which you need to satisfy, the available number of combinations to you are always n factorial. The combinations here you will have are always n factorial, right? So for n is equal to 3, n factorial. For n is equal to 4, we have 4 factorial combinations which we need to try. For n is equal to 5, 5 factorial combinations we have to generate. And for each combinations, you need to check if the condition is satisfied or not. So that is one brute force approach. But if you go through this brute force approach, the problem is that every time you have to do n factorial comparisons. Every time you do, you have to do n factorial comparisons. But there is another approach which we call as backtracking approach. What is that another approach we have? We call it as backtracking. So inside backtracking, instead of exploring and generating all possible combinations, what we do is we keep on generating a solution. At any point of time, if we find that the combinations which were generated is not leading to a solution, what we do is we backtrack. And when we backtrack, we revert our decision so that when I proceed further in my direction of recursion tree, it would lead to a proper solution, right? So let us do one thing. What I'll do is we will not write our algorithm based on brute force approach, but rather we will use an approach called as backtracking. So in this backtracking, let me show you how this backtracking example works. Okay, so I'll just remove them. I'll show you the approach, then we can write a program for this. Okay, so what we are saying that we have a brute force approach where we'll generate all combinations, and once we generate combinations, we explore each of that combination and we check satisfy or not. The problem with that is we have to try for n factorial. So I don't want to do n factorial. I want to do an approach which would be less than n factorial, but at the worst it would be still n factorial. So this backtracking approach is far more better than brute force approach. So let me show you how the backtracking works. So in case of backtracking, what I do is, so I initially start with row wise. Remember how I am proceeding? I am proceeding row wise, right? This is how I am proceeding. I am proceeding row wise. So I initially start with first row. What I do? I start with first row, then I will first find a position for Q1, then I will find a position for Q2, then I will find a position for Q3 and Q4. What I'll be doing is, what I'll say is that Q1 has to find a position inside row 1. I'll put this one condition. This is already implicit. Q2 should find its position in row 2. Q3 should find its position in row 3. Likewise, Q4 has to find its position in a row 4. This is fixed. So we will go on this approach. Okay. So what I'm doing is initially I'll find a position for a Q1, then I'll find for a position for Q2, Q3 and Q4. Fine. So what I'll do is this, when I want to place Q1, I will start with the first available location. Can I place Q1 at this first available location? So I will place Q1 at 1 1, and I'll see if is there any queen in the attacking position at 1 1. So do I have any element in the column wise in the first column? No. Do I have any other element in this the first row? No. Diagonally, do I have any element here? No. So I can place Q1, right? So once I have placed Q1, I got a position for a Q1, then I will move to the position for Q2. So for a position for a Q2, I'll start with the first available location. What it is? The 2 1. So I have placed it. Then I am checking if I can place it in this column. So when I want to place it in the first column, I find Q1 in attacking position. So what I do? I now move this. I now move this to second column. So once again, I'll check, is there anything in this column? No. Is there anything in this row? No. But if I check diagonally, there is one queen which is in attacking position. So this is also not a valid position. What I do, I cut this from this location and I search for next location. What it is? Q2. So is there anything in a column? No. Row wise, no element. Diagonal wise too, I do not have any element. So this I found out a position for Q2. Now what I do is I now try to find out position for Q3. So when I want to find a position for Q3, the first position I try to keep it is at the first available location. Can I keep it? It is in attacking. So what I'll do, I'll not put this here. I'll put it here in this second column. Is there anything attacking queen in column and row wise? No, there is no attacking queen column and row wise, but diagonally Q2 is in attacking position. So this is not a valid position. What I do, I now move this and I now put it here in this third column. Q2 is column wise attacking. So even this is not a position. What I do, I now put it here. Is there any attacking position? Yes, Q2 is in attacking position. Now tell me, I am done with exploring all position for Q2, but still I cannot find a position for Q3. So why is this possibility? This is because I have placed Q1 and Q2 wrongly. That's why I cannot find any position for Q3. So this, my inability to find any position for Q3 is because I have placed Q2 and Q1 wrongly. So I have to position them correctly so that now I will get a position. So my earlier choice to put Q3 might be wrong, or my earlier choice to put Q1 at this column 1 might be wrong. So what I do is I do a backtracking now. So now look at that. The point at which now I'm moving back, this is called as backtracking. The moment I lead to this solution 3, the moment I find I cannot generate any solution, what I do, I just go on backtracking. So when I do a backtracking, you can see that I'm just doing Control Z. So this position, okay, position which I was looking for Q2, this was wrong. So what I'll do, this position, if I place Q2, yes, though it is not attacking with Q1, this was leading to a solution where I cannot find any position for Q3, right? So what I'll do is I will not put it at Q2. What I'll do, I will now move it to the next location, Q2. Now I will try it for Q3. So the first position Q3, can I keep here? No, I cannot keep here. Can I keep it here? Can I keep Q3 here? So diagonally, no element crossing, row wise, column wise, no element is crossing. That's fine, right? So I could now find out a position for Q3. So once I have found out a position for a Q3, which is not attacking with any of the earlier Q1 and Q2, I will now go for Q4. So the first available position for Q4 is this. Can I place here? No, I cannot place here. Then the only possible here. Can I place here? No. Can I place here? No, because Q3 is in attacking position. What I'll do, can I place it here? No, I cannot place it here. So I cannot find a position for Q4. I cannot find a position for Q4. So what I do, if I cannot find a position for this, could be result of either placing q3 in a wrong location, or it could be a result of placing q2 in a wrong location. So what I'll do, I'll do a backtrack. So from here, I'll do a backtracking. So this couldn't be a position for q3. What I'll do is, I'll try to position q3 here. Can I place q3 here? No. Can I place q3 here? No. So I cannot find any position for q3. So what I'll do is, I'll do a backtracking now. So even this is wrong. So what I do, q2 is also so earlier q2 was at this. I found a position. So now I cannot find any new position to q2. What I'll do, I will backtrack. I'll backtrack and I will now come back to the first position. So the earlier decision of positioning q1 at first position itself was wrong. So what I'll do, this decision I'll backtrack, then I will find a new position for q1. After finding new position for q1, once again I'll look for q2. Can I place q2 here? No. Q2 here? No. Can I place q1? No. Here I can place q2 here. So once I have placed q2 here, now I'll search for position q3. Can I place q3 at first position here? Yes, I can place q3 because it is not attacking with any of this position. So now once you have found out a position for q3, you will try to find out a position for q4. So can I place q4 here? No. Can you place here? No. Can you place here? Yes, you can place q4 here because it is not attacking diagonally rows or column. So this leads to the solution of the problem. Now in this problem, if you look at this problem, we have not explored all possible combinations. So this is how it works. I'll show you. There is a concept called a state space tree. So it is 3, this is 4, right? So in the state space tree, what happens is, you start finding a position for first row. So first row, if I say 1, for example, if I say 1 here, let me write this. So I can represent this chain in terms of backtracking. So initially I have position q1 at 1. If I place q1 at 1, what I can place at 2? So here I can place queen 2 at position 2, and at position 3 I can place queen 3 can be placed at position 3, or queen 4 is placed at position 4. So for this chain of this tree, I'll show you what values represent this. Let me write it in this order. For example, q1, I'll just take them in red color so you'll understand what exactly I'm trying to say. What is this representing? So this tree, so queen 1 at position 1, queen 2 at position column 2, queen 3 at, see, queen 3 at position 3, queen 4 at position 4. This is one combination, 1, 2, 4, right? So if I place queen 1 at this can have various combinations. I'll tell you. Queen 1 at position 1, queen 2 can now take any of this position at 3, queen 2 can take any of the position at 4 as well, right? Queen 2, if queen 1 is placed first, queen 2 has this any of these 3 possible combination. It could be at position 2, 3 or 4, right? Then if I consider queen 2 at position, let me show you what I'm talking about. So now if I talk about this position, I'm talking about this tree, the 1, 1, 3 and thus. So if I have queen 2 at position 3, then 3 can have position 2, then 4 can have position 1. So this can have two more combinations, 1 and 2, right? And for 4 you have see, for this 2 you have 1, for 2 this could be 4 and this could be 3. So for 2 and for 4, if you position queen 2 at 4th position, then at 3rd position queen can occupy either 2nd position or 3rd position. On 2nd position you have combinations 1, not 1, it could be 3. So it could be 2. So now if you look at this, how many combinations I have? This is one combination, 2, 3, 4, 5, 6. The same combination can be even there when I have 2 at this position. So 6 for when 1 at this, when queen 1 is 1 position. Same if queen 1 is at position 2. Same 6 combinations. Same 6 combination if when this is at 3rd position. And same 6 combination if queen 1 is at 4th position. So these are various combinations which I get. So overall, how many combinations I get? 6, 6, 6. How much it is? 24. And what is 24? Is 24 equal to 4? What is 4 factorial? 4 factorial is 24. Yes. So this is how we get. So now when we do one thing, I'll tell you what exactly we are doing is. So in case of backtracking, what we do is I position queen 1 here. Then I find a position for q2, right? So in my case, for example, if I talk about q1, if I talk about this red combinations, right? Let us just consider this red, q1, q2. So q1 is placed at 3 and q2 is placed at position 3. I mean, I'm searching for this combination, this 3, 1 and this 3, right? This 1 and this 3. If I do this, then if I see, when I say backtracking, what I'm doing, I'll tell you. So we come to this chain, we come to 4, and if I find this is not a valid solution at this point, what I do, I backtrack to this point, then I start exploring this. Then I come, the moment you reach to the depth, it means that you can find a solution here. So every time you check this combination 3, 2, if it doesn't work, you come back, you start checking this. When I say backtrack, you are coming back. You are checking what if the 2 is placed at 4th position instead of 3. If it is placed at 4th position, then 2, 3 can have these possibilities of this. If they cannot be placed till now you have reached, but still you do not find a solution, what you do is you backtrack here, then you start exploring the other branch. So this is called as backtracking here. And whatever the diagram which I have drawn, this is called a state space tree. What I call it as state space tree. Okay. So what I'll do is, there are a lot of available lectures on n-queens problem which tell you this state space tree, what is the state space, how do I put this and all that. But there isn't any literature available, good literature available, which will teach you how to write a program for this. So what we will do is we'll try to write a program for this. Fine. So before I write a program, so what I'm trying to do is we'll write a program which will place these queens in a perfect position, the position which we wanted. So we'll write a program for this, a recursive program. And once we are done with the recursive program, we will explore what could be the iterative version as well. But remember, whenever you say backtracking, it will 100% surely involve recursive programs. And it is always better to write backtracking programs in recursion and then go for iterative. We cannot directly write iterative programs for backtracking. So it would be very counterintuitive and very difficult to understand. So before I go with the program, just a quick question. Have you understood this? Okay. See, if you feel typing is a little bit takes time, you can just raise a hand and you can lower it. I think that would be far more easier. Okay. So I hope you understood that. Specifically, I want you to the approach which we have looked at. Like we were not able to position Q2, and then we went when we backtracked, then we kept it. So if you understand that, that's fine. So for time being, I'll just delete this whatever the thing which we have done. Okay, so I hope you have understood this logic. We started with position 1, it was an available position. Then we looked at Q2, it was fine. We find location. So the moment we cannot find any position for Q3, then we go for backtrack. And when the moment we find for Q4, if we do not find position, we backtrack and we check that. So there could be a case when you do a backtracking and you explore all possible combinations, still you won't get any solution. Then it's a case where you will say that no such combination available for this specific board. So that will happen for a specific type of problem. We'll see it when we write a program. Okay, so let us write a program. I'll just open my PyCharm window. Can you think of recursive logic? It will be definitely a recursion one. Let me type the program for you, and let us see, can you get the programming logic there in the recursive program there. So I think we have 30 minutes. I think 30 minutes is enough to write a program. It won't take much of length. Since we're using Python, it won't take much of time. Okay, I hope you can see the PyCharm window. Do you see the screen? PyCharm screen? Can you see my screen? Okay, fine. Okay. So let us start with n. Let's initialize n with some values, right? So what we will do, n to denote the n of n queens problem. Okay. Once we create n is equal to 4, we have to create a board. And what would this board contain? The board will contain a n by n grid, and initially we will initialize this board with all zeros, and wherever I have to position a queen, I'll just say it as 1, right? So we will create a board. Board will be of size n by n. What I'll do is, so I will use list comprehension. So create a board of n by n size and initialize it with 0. Lies it with 0, right? So what I need to do here, 0 for I in range n, and this will be for I in range n. Hope you are getting this. What this will do, this will create a board of let me see what it is creating. Okay, so it is creating first row, second row, third and fourth, n by n. Okay, I'm getting the board now. So now since I'm getting the board, what I'll do is we have to look for the position of placement in that. Now, before I look for this position of placement of this row and all, before I write the iterative logic, remember, every time I position a queen here, what I was supposed to check, I need to check if there is any element in this row or in this column, right? I need to check for that. Plus, I need to even check for whether there are any elements diagonally or not, right? So let us spend a time and see what exactly I can do there. For example, I think let me explain it here itself. So if I do let us suppose I copy this and I'll tell you what I am trying for. See, this is row 1, this is row 2, row 3 and row 4, right? So our board is this. Now the issue here is okay. See, initially I will place my queen here. If I find a position for queen 1, right, I'll check for the row and column, and then I will check for position for q2 in row 2, position for q3 in row 3, and position for q4 in a q4. Now tell me, if I position q1, what I have to check and what is not necessary. Do I need to check if there is any queen in this row wise? If I make a condition that q1 will be always in row 1, but it might be in any of this column. If I decide q2 will be always in a row 2, just it might be in any of these columns available in a row 2. If that's the case, what should I check for? If I am at this location, for example, if I'm at this location, what is something I need to check and what I am not supposed to check? Even if I check or not check, it doesn't matter. I need see, do I need to check if there is any queen in this row or not? When I'm trying to find a position for q2, should I check that is there any queen in this row 2 or not? Obviously q2 will be in a row 2. I need not check this row. What I need to check? I need to check if there are any elements in this. For example, if I check for q2 in this column, for first column, I need to check if there are any queen in this already placed in this column or not. So in this case, if I want to check in column wise, if I'm at row 2, I have two possibilities. Check for rows above it, check for rows below it. What is redundant? Can any student guess that? I am trying to find a position for q2. I need to do condition checks. The first thing is I need to check if there is any queen in this row or not. That I will not check itself because I know that only q2 will be placed in a row 2. I will be never placing any other queen in this row. So I will not check for any queens in this q2 or not. For example, let us suppose I have already positioned q1 here. Assume that q1 I have given this position. Now I am looking for position for q2. I will start with this. If I start with this, I need to check if I can place it here or not. If I want to check if I can place it or not, I need to do some checks. What's the first check? No element should be in a row. This condition I will not check. Why I'm saying? Because q2 will be in that row. I am very damn sure that there will be no other any queen in this one, because I have reserved this row, reserved this second row for position for q2 only. Then only conditions which remain for me to check are are there any queens already placed in this column, the column 1? So in order to check for that, tell me, should I check for the rows above this, or should I check rows only below this, or should I check all the rows in this column? For first column, should I check all the rows, or should I only check the rows above the current position, or should I check the rows only below it? If I want to ascertain that no queen was placed in this column earlier to this, can you reply that? I want to see like how you can get the logic. Yeah, Mohammed has said that yes, Mohammed and Sumit, yes, above and below at current position. See what Mohammed is saying that I can tell that you have to only check for above. What I am saying is that I am saying that I need not check the below columns because I have not yet placed any queen for it. See how I'm doing position for Q1, then position for Q2. When I'm trying to find position for Q2, I am just finding it for Q2. I'm not finding it for Q3 and that. When I try to find position for Q3, it will be dependent on what position I gave to Q1 and Q2. When I'm trying to find a position for Q4, it will be dependent on what position I gave it for Q1, Q2, Q3, right? So what I'm saying is I need to only check for the upper rows. That's it. I will not check for below rows. So I'm trying to save the computations. Likewise, if I want to check diagonally, for example, let us suppose I have placed Q2 at this. Now I want to find out, can I place Q3 or that? For example, if I place, I am checking for this location for Q3. Column wise, I'll only check for above two ones, above two in the same columns. For all the rows above the current position, I'll only check these columns. Column 2, row 2, column 2, row 1. I'll only check for this above 2. For diagonal, tell me, is there any need to check this below diagonal values, these two values, when I'm trying to find out a position for Q3? On the same logic, I need not check for element diagonally lower than the current position. What I need to do, I need to always check for these diagonals available at these diagonals. I need not check because I have not yet found out any. I will be placing it in future. I have not placed anything there, so I need not check here. You have to always check diagonally upperwise, this cross and this cross. That's it. I hope you're getting that. Have you understood what I'm checking for? So let me 10, let me write that. So what I'll do is we will now define two functions which will do that checks. What I'll do is definition check column. I'll only check column. So in order to check column, what I do is I'll be providing the board to it. I'll be providing the row and column at which I am there. And this function should return me true. This should be true if on a board at this row and column, if I can place the queen. If I cannot place the queen at this row and column on the board, then I need to return false, right? So I'll be checking for column. Likewise, I'll have to check for diagonal as well. So I will say board, row, and column. Here too, if I can place it diagonally, so this is column check, this is diagonal check. If both these functions return true, it means that I can place queen at that specific position. If I can, if any of this returns false, it means that I cannot place it. Then I need to search for next position, right? So first let me write this code for this. So when I get a board and row and column, what should I check for this? I need to check for all the columns above that. So what I'll do, for I in range, I'll write something here, then I can fill. If, if, if board of, what I'll be checking, what will be fixed here? I need to check column. So column for I, what I is, what is changing? I is row. So from given row, I need to check for all upper rows in the same column. Okay, I am at here. I need to check for this value. I need to check for this value. So I was past this row column. What should be inside this range? Here it would be row, and this will be in a decrementing order, right? So till -1, what this will do, this is a range of for loop which gives you a decremented values. So if I say, if I am at here, this I will iterate at this location and then this location till I reach 0, right? And what value will be I'm looking for? I and column. So I'm keeping column same. I have to just check if it is equal to 1. Remember why I'm checking it for equality of 1? Because if I place somewhere in a queen, instead of 0, I will write 1. So you need to just check if there is any 1 already placed. If it is 1 means queen is already placed. If it is 0 means no queen placed. So if in any of this earlier column, if you find 1, it means that already something is positioned in that. What you will do? You will return false. Safely directly return false. If you do not find anything in this loop, when you come out of this loop, probably it is an indication that there is no such queen placed in that column earlier to this. So you can safely return true. Right? Now it is a question of diagonal. Okay, tell me how I should check for diagonal. So now for a diagonal, let us suppose I am at this position. You need to check for diagonally this value. There should be no 1 in this diagonal value, and here too there should be no diagonal value. I hope you're getting this. Okay, so how do I generate these values? I need to check this 3 locations, and I don't want to hard code something. Can you do how I am at this row and column? So if I am at row and column, how do I get this location? Row minus column minus, row minus column minus. And how do I get these values? Row minus column plus. So this direction, okay, how do you get this direction? Row minus column plus, row minus column plus, row minus column plus. How do you move this top left corner? Row minus column minus, row minus column minus. So you need to check these 2 conditions here. So let us check first top right corner for now. Here what you need to do is you need to generate combination of 2. Okay, so what I'll do is I'll show you quick. I'm not sure if you have used it or not. Have you used zip function in Python? Can you tell me quickly, have you used zip function or not, so that I can quickly move ahead? Do you know what is zip function in Python? Okay, so quickly I'll tell you what I'm getting that. For example, okay, so if I say for, let me do one thing. What I'm saying, for I comma j in, or else what I'll do is I'll take 2 lists. L1 is equal to 1 comma 2 comma 3 comma 4, right? I'll take L2 is equal to 5, 6, 7, and 8, right? This is L1, this is L2. So if I say, let's say L3 is equal to zip, what I'm saying, zip L1, L1, comma L2. And now I want to print each element of this. So for I in L3, print I. What output I am getting? So what are there inside L3? 1, 5, 2, 6, 3, 7, 4, 8. 1, 2, 3, 4, 5, 6, 7, 8. What is this? 1, 2, 3, 4, 5, 6, 7, 8. So what you get is you get a tuples. First element from list 1, first element from list 2. Next tuple. Second element from list 1, second element from list 2. That's what you get a tuple from this. Are you getting this? So this is how what zip does. It gives you tuple. If I make zip of L1, L2, L3, then I'll get first tuple. It is like first element of both the lists, second elements of both the lists, third elements of both the lists. That's how the zip function works. So it's a built-in function. Are you getting this? So now what I want to do here is I want to generate these values in a zip function, I comma j, and I comma j, right? So just look at this and let me know. I hope you should understand now. For I comma j in zip, I'll say two range. For the first range and the second range, I want the set of column ranges. See, if I want to move to left top, how should the row values do? Row values have to decrement, right? Row values have to decrement, and even column values have to decrement. So from the current row and column indicated at this location, row has to decrement, column has to decrement. So what I'll do is I'll generate the possible row values, possible column values. So what will be the row values? Row till -1, this is a decrement loop. Likewise, I'll also do it for column minus till -1 decrement, right? I get this value here. Now, when I say zip of this two lists, what this list will give you? This will give you the decrementing row values. This will give you the decrementing column values. When I say zip, it will give me a tuple. So for each I and j, tuple of I and j in this, it denotes one position. The first position, the decrement position, till you reach to the end of this matrix. So for each of this, what you need to do is, if board of I and j equal to 1, what you need to do? Return false. This is 1. What this is doing? Diagonally moving towards top left, right? Likewise, we'll have to write for, you didn't find anything to the top left, but there could be something to the top right. So for top right too, we'll have the same loop. We'll have the same loop. But now tell me how. Columns, row is decrementing. Row is decrementing here. For example, let me tell, row is decrementing. What is incrementing? Column is incrementing. So what should I do here? Row is decrementing. Column is incrementing. So column is incrementing. I hope you're getting that. So column is incrementing, and what could the maximum value the column can take? N, exclusive N. You need to just check I and j. That's it. If it is, return false. And if none of this you encounter any returns, in the end, finally you will return true, indicating that there are no elements either diagonally to the top left, either diagonally to the top right. So these are the two functions which will check whether a queen can be positioned safely at that location or not. Okay, so have you understood this till this point? How I'm moving to the left and right? This is generating a tuple pair values. Uh, in check underscore column, what is in the check underscore column, why we are not incrementing the column? So to the question Mohammed has asked, see, I am at this location. We have agreed that we will not check any values. Then I need to check if I want to fix this position. I need to check if I have placed queen somewhere here. For example, if I already placed queen here, or queen 1 was placed in third column. If I want to check here, what I need to do is I need to check only this column values. Is there anything or that? So what I do is row decrement, means I'm checking this value. Is there any queen placed in that column? For q3 no, for q2 no, q1 yes. So that's why I do not decrement column remains same. I am only talking about this column. If I want to get these three values here, I need to decrement column. Row remains column remains same, row decrements. I hope that has come. So this will be done. Remember, I am just checking for safety of this. Whatever the code I am doing, check column and check diagonal, I am only checking for safety of this. But in our next logic, we have to check for this movement as well. What if I place this? If not, what if I place this? If not, what? What if I place this position? That we need to check in. That logic is still pending. We have to write that. Okay. Okay, so we have written this two. These are safety checks. Like if this are true means I can place that. Okay. So now what we need to do is we need to write our actual backtracking logic. Backtracking logic. Okay. So what we'll do is we have to iterate through all n positions. We will start with first n location. So what we will do is and this will be the recursive function. So what we will do is we will write a function n queens, and to this I will give a board, and what I'll do is I will give a starting row at which I want to start. I'll just give a row because I'm starting with queen 1, queen 2, queen 3, queen 4. That's what I'm doing that. And I'm not bothered about columns. Column check is done internally. So what I'll do, board and row. So now for each, what I need to do is for each of this, remember for I in range n, for I in range. So now what I want to do is now I want to look at, I'm starting at this. Now I need to iterate this column wise. I need to check where I can place in that. So when I first give this row and that, what the first thing I'll do is I have to first check if I can place the queen at the current position. What is that which I can check for the queen at current position? So what I need to do is I need to check column, check if the column for the row for the column I, right? So let us suppose I am at row 1. This will iterate for all the column position. Row 1, column 1, row 1, column 2, row 1, column 3. That's what I am checking that. So now here I am checking for these values. Move it for all. For each cell, check if they are diagonally column wise and diagonal wise. It is safe to position the element there. So if check column for row is equal to true, and I need to also check diagonal board at row at column means I, if is equal to true, yes, if it is true, it means that if this condition is true, it means that I can place the queen at that current position, right? So if I can place it means what I need to do, board of row of I is equal to 1. I can place it. That's why I'm saying 1. Once I have placed it at the specific row, what I need to do? Place it. If I place it at specific row, place it, then call for next n queens. Next n queens. I can place it for this one. So call for next row, board, comma, now it will be row plus 1. Right? If I can place a queen at any of this I, when I'm iterating in that, if I'm iterating in that, if I can place it anywhere, then set that column as 1. So I was looking for this value, I was looking, yes, I can place here. Then what I'm doing, I am making it is 1, and I am asking my n queens to solve for next row, right? So this is what the next row call I'm making that. Are you getting that? If the, now tell me, now if I, the way I looked, for example, see, initially when I write my this program is 0 here, so initially this will be 1 and 1, the first column can be placed. Then for q2, when I make call for this q2 here, board and row plus 1, I'll go here, then I'll go here, I cannot place here, here I can place. The moment I place here, the result of this call, if I can place this value, I need to return true. If I return true, then I will move to the next column. If I return true, then I'll move to the next row. Are you getting that? If I can place, then I'll move to the next row. If I can place, then I'll move to the next row. If I cannot place, I need to return back. If I return back, I need to continue my loop. If I return back, I need to continue my loop. So how do I do this? What I'll do is I'll assume that this function will return something. If n queens of is equal to, let us suppose if it has to return some value, or I think the best thing is to just put it in this. If it is, if I can place, if this method has returned true, if this method has returned true, then I will return true from this method, right? So I have called this position. So what I'm saying, the position at which, when I will make it fix, when I can place any queen in the next row. If I can place any queen at this next row, it is indication that I can use this, the previous position. If I get a response from this next row that I cannot place any element, then this my choice is wrong. So what I need to do is, I need to revert back this my choice. So if the placement of queen in next row is returned false, then I need to repeat this loop with the next position. So here we are talking about something backtracking. Okay, so what I'm doing, if n queens of board plus 1, if it has returned true, then I will make return true for this call, this loop. If this returns false, let us suppose I cannot place any queen in row plus 1. If I cannot place in row any in this one, what I do is, when I come out of that loop, when I come out of this if, when I come out of this function call, when I come out of this function call, I'm checking if this function call, was I able to place the queen in row plus 1. If I can place it, then this function would have returned true. If it is written false, means what I need to do? If it is written false, means the earlier assignment which I made it is 1. I need to revert back. What I need to do? Board. I need to just revert this decision back. And I need to say 0. So what I'll do is I'll make 0. I have found one position for this, but in next row I cannot place the queen. So what I do, I come back, I set 0, and this loop will go again, and I'll now repeat for next I in this. Maybe here it didn't work, but what if I make 1 here, and now I will ask my next function to find position. If it finds, this returns true. If this returns true, then I go for this position. Here, if I cannot place anything, for example, if here and I cannot place anything, this will backtrack here. This will go for this 0 and it will go for 1 and it will ask check. Now check if you can place the queen row or not. If it can, let us suppose if it can place somewhere here, it will go and it will ask for next row, see can you place it or not. With this combination, if it cannot find any position for this, it will say false. Then it will say probably I might have gone wrong. I will set 0 and I'll continue my loop 1 and then I'll ask it for find position. If it is not, I'll do one thing. If here it is not, then what I say, I cannot place anything here. So I'll once again go back and I'll come here. Here I cannot place, I'll go back and I'll say, then what I'll do is, I will now say it is 0, it will 0, and I'll say 1. Now I'll find a position for row 2. So when I make a position for it, will once again find a new position in row 1 here. Maybe it finds it somewhere here. Then it will do it. That's how we are doing the backtracking. The backtracking logic, exactly what we have discussed that. It might seem little bit very complex to understand, but if you could recall that with what we have seen in the diagram, the Q1, Q2, then we did a control Z, then we found this is exactly working on this. Let us suppose even after trying for all the combinations of this, after trying for all the columns, let's suppose after trying for all the combinations, you did not find any of the safe position at the end, what you will do? If you are not able to find any column at the end, what you will do? You will return false. So if you return false, so when I was talking here, right, what this will return true and false. There is a case if this row plus 1, if it iterates to all the 4, but still it is not able to find any combination, then it will return false. Then it will come back, it will continue the loop. Right. So these are the conditions. But remember, somewhere it has to stop. What will be that stopping condition? So initially our row is 0. Then it has asked for row plus 1. It has worked. So what it is that you have found a position for Q. It has worked. You have found position for Q2. Fine. You found a position for Q3. Fine. Found a position for Q4. Fine. If technically when you are going through this, if you find here that you have found a position for this, my loop will continue and it will ask for, and it will make a next recursive call, right? It will make a next recursive call if it has successfully found a value for this, right? So here, when you have exceeded this n, when there is a next recursive call to find a successful position for n plus 1, here we are at n. So when we get that to next row, it indicates that we have already found successful positions for 4. When would this call for next call go? This call would go only if you found a successful position for this column. So when you found a successful position for this column, it is indication that you have found positions for all n's. So this would be the base condition or to the break condition. So whenever you get a call where the row is equal to n, since we are at 0 indexed, since the list of lists is 0 indexed, since list is 0 index, I check for n. If row is n, it means that I found a solution. What you do, just return with a true. So it will automatically return back and it will just complete the loop, entire loop. So this marks the n queens. Now let us try this. Let us try this and let us see what result it prints. Okay. So what is here n? My n is equal to 4. Fine. How do I execute this? N queens, board, and row 0. That's the call. Call the n queens. Then how do I print the solution? Let me print it in a column wise. So for each row in board, print row. This will print in a a matrix format. Print the board. Okay, so for n is equal to 4, let us see what output we'll get here. Okay, let me comment this earlier print. I'm not sure if is it generating the solution. Is it generating the solution? This no attack, no attack, no attack, no attack, no. It is generating solution for. Do you say this is generating a solution? Do you agree that the output is right? Okay. Let me make it for n is equal to 5. Okay, this is n is equal to 5. Tell me if it is right. Tell me if I have missed something here. This one. Okay. This is 1. Check diagonally also. There should be no 1 in diagonally also. Okay. This is no. This is no. This is diagonally no cell, no column, and this one. No cell, no this. Okay. For 5 also we are getting this value. Should we increase this? Let us make it for 8. This is for 8 query. N is equal to 8. Can you confirm if it is matching or not matching? This is for 8 queens. Do you agree that it is a correct solution? It should not match anywhere. Okay, so I think this program is working for n is equal to 8. Okay, tell me what will be the value for n is equal to 3? Can you find any position for n is equal to 3? For n is equal to 3, will there be any solution for n is equal to 3? What do you think? Will there be any solution for n is equal to 3? Yeah, so for n is equal to 3, there shouldn't be any solution. So let us see what solution our program generates. Our program should also generate solution when n is equal to 3 as well. So what will be the solution window if n is equal to 3? It should be 0, 0, 0 if n is equal to 3. Our program should work for n is equal to 3 as well. Let's see what output I'm getting. Okay, we are getting 0, 0, 0 means I cannot find any position for any of these cells. So the recursion trace and calls was right. If we had messed up this return calls, this should have not worked for n is equal to 3. So for n is equal to 3, I get this. For n is equal to 2, will there be any position for n is equal to 2? For 2 also, I think we will not get any solution. For n is equal to 1, for n is equal to 1 means 1. Yeah, for n is equal to 1, I get one solution. Okay, so let me go back to n is equal to 4 and let me execute this. So you should now get the solution. Okay, now, yeah, so I think we have exceeded our lecture time a lot. So a quick end question. Have you understood? The theory part you might have understood, that N1, how to do it and that. My concern is, have you understood the program? Okay. So all those who have understood program, can you raise your hands? I can quickly get an understanding how many of you have understood this. Okay, Sumit, yes. Okay, 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 good. Yeah, yeah, sure. So it's good that you understood the program. So what I'll do is I will share this program with you. This recording is anyhow, I'll share this, and I'll also share this with this program as well. See, the problem with now, what I want to say is that when you go and try for n queen's problem on YouTube, search for n queen's problem on YouTube, you will get a very good videos which will explain this combinations, which will explain this hours of n queen's videos, which explain the theory of that. They will always explain you theory that place queen here, go back 5 cells and that. And I don't think there is any nqueens video on YouTube which tells you how to write this program. And the problem with most of theory is that theory is always easy to understand. When someone asks you to write a program, that's where the true developer comes out. Fine. So once again, as I'm saying, whenever you try any algorithm, try to write a program that will clear your concept. So in tomorrow's lecture, we will spend a time on complexity of this approach. Can you quickly tell what's the complexity of this approach? The complexity of this backtracking approach will be O of, see, at the max, how many backtracking I'll do that? At the max, the maximum backtracking will be n factorial. We will discuss what it is. Okay, we'll discuss why it is n factorial. And there are some brute force solutions where the complexity could be n to the power of n. N to the power of n. So do you agree, is this polynomial order of complexity? No. N queen problem, what are the approach which you have seen? It is not in a polynomial. This is exponential, non-polynomial complexity. So this is a problem where we do not have any polynomial approach. Okay, so I'll upload the program and I will also share the recording. Go through this. Then if you have understood this, now I think you can easily implement Sudoku problem. I hope most of you might have already solved Sudoku problem, but the solution to Sudoku problem can be very efficiently generated by using backtracking. Just think of that. That's why I've given you this assignment on Sudoku problem. Spend time on this. If you do not get, let us work on that. How we can generate a Sudoku problem based on backtracking. The concept is exactly same. Fine. I think I have taken much of time. And I think Medgar sir was saying that most of your class has not given a feedback. So make sure that you give the feedback. It is important. So complete the feedback if someone has not given the feedback there. Fine. So that's it for this lecture. I will share the recording later in the day. Fine. I think you should be fine to leave.